All right. Welcome back, everyone, to our next Geophysics and Tectonics seminar. I'm happy that you could join us this week. And I'm excited to announce that our speaker this week is Walid Ben Mansour, who's currently a postdoc at Washington University in St. Louis. So whenever you're ready, Walid, please take it away and talk to us about the thermochemical structures of the Gondwana terranes.
Okay, thanks. So we just switch my video because I don't like to see me. Okay, so thanks Kelly for the invitation and giving the opportunity to show a piece of work I'm working on now since 2018 when I was postdoc at Sydney, so at Macquarie University. So within the next 45 minutes, I will try to introduce a little bit the method and the idea behind and discuss about thermochemical structure of Gondwana terrane. So like most of you know, Gondwana was a supercontinent that exists about 500 million years ago and began to break up about 200 million years ago with the opening of the Drake Passage separating South America and Antarctica. And it was formed by the accretion of several craters. So on the left, we have a map from March 2011, where we can see the West Gondwana part in blue. So we have the Amazonian crater, the Sao Francisco and Rio de Plata shield in South America. We have the West Africa, Sahara Meta crater, the Congo crater, Tanzania crater, and we have two little blocks, the Zimbabwe and the Cape Verde crater. They form the Kalahari crater. So this bluish color block here is the West Gondwana part. And on the east one, so the yellow is the Madagascar shield, the India shield, East Antarctic shield, and we have three blocks for Australia. So the formation of Gondwana began about 800, 600 million years ago with the East African orogeny. So the collision with India, Madagascar, and East Africa. And it was complete 600 million years ago with the collision with South America, Africa, and in the south, Antarctica and Australia. On the right is just a paleo reconstruction of the last 2 million years ago of the Gondwana on the Gondwana continent. And the blue triangle here is the hotspot location. So we'll discuss later what will be the effect of this hotspot on the thermochemical structure of the Gondwana terrane there. So the work I will show you today is a piece of a large project and is a combination of several small projects. So between 2018 and 2021, I'm working mainly on the Central and Southern Africa. This was a project is an RC linking project between Macquarie University in Sydney and the mining company De Beers. So Juan Carlos Alfonso was my advisor at Macquarie University. Andrew McDonald and Nico Januska was the contact with De Beers company, mining exploration. And Inje Young, I collaborate with him for the seismic part of the project. Now I'm working in St. Louis with Douglas Wines on the Antarctica continent, and we collaborate with a colleague from Lehman, so Andrew Lloyd, colleague from Stony Brook, Wilson Chen, and a grad student from my department, so Zhang Yangzhu. And a small little project for South America, where we try to have an idea of the thermochemical structure of the continent and compare what we can observe in South America with what we have for Central and Southern Africa. So these two projects was money to work with, and this is project for free, I will say. So in this presentation, I will focus on cratonic mantle property. And for geophysicists, cratons are generally defined as boring. They host the oldest rock on Earth, and they show no deformation for a long period of time. They are defined as a cold, thick lithosphere, so generally up to 200 kilometers. In terms of bulk composition, so chemical composition of the mantle, they are defined as depleted lithospheric mantle with higher magnesium number we use as a proxy of this to quantify this depletion. And they also define with a dry cratonic root to explain this very long-term evolution of the cratonic roots there, why we have very thick lithosphere, cratonic lithosphere beneath craton. On the right is a map from Pearson and Wedding 2014, where we can see the location of the cratonic block from geological observation. On the right is a shear wave velocity model from Schaefer and Lebedev 2013 for different depth. And we can see the correlation with this high velocity anomaly, darker bluish color associated mainly with cratonic region. So we can locate easily where is the West African craton in Africa, also the Gondwana and the Kalahari in Africa, but also the very clear signal in North America, for example. But this whole picture, however, several studies from geochemistry and geophysics observation showed this whole picture of cratonic mantle means very undeformed and always the same for the long period of time is completely wrong. As you can see, for example, a paper from Griffin et al. 2003, where they look at the evolution of the lithospheric mantle beneath the Kalahari Craton, so in South Africa. We have also some study from Foley 2008, where they look at the erosion of the cratonic roots, but also other study, mainly in Africa, because it's the region where there are more data in terms of seismic, in terms of geology, and also the relationship between extraction there. So now if we look a little bit some geophysical observations, some large scale feature. So let's start with the topography and look at first, for example, the eTopo1 model. So this is the elevation map on a large scale. And we can ask ourselves which mechanism can support the present day topography of this region. Why we have high topography, for example, where we are very old cratonic block, like for example, in Kalahari Craton or in Tanzania, in India, also in South America. What could be a mechanism can explain that if you just look the surface expression of that. Then if we look at information from the density distribution within the mantle. So here is the geoid eye anomaly associated with the uppermost mantle from Alfonso et al. 2019. So we can highlight the positive eye anomaly where we have high topography and this idea of dynamic topography. So for example, in Angola or also along the East African Rift, but also in South Scandinavia. And we can also explain the lower anomaly as a consequence of the presence of this high positive anomaly. But I'm sure in the audience we can have some experts and more people have experience about the geoid interpretation and could comment more about this kind of feature there. So now if we look at that kind of data set like the heat flow model, so here is the model from Guter Beta 2011, we can see a very clear signal associated with cratonic domain. So we have generally low heat flux production, for example, in North America, in West Africa, but also in Siberia or in West Australia. And this signal generally comes from the crustal bug composition there. So the crust associated with cratonic domain are also very specific in terms of bug composition. But as you know, so keep in mind that this kind of large-scale map for heat flux is also biased by the number of sampling. So there are some regions are very well constrained, like North America, and there are other regions are very poorly constrained, like in Congo, also in Antarctica, where probably we have lower value for the cratonic domain in Antarctica, but because there are not enough sample, it's just interpolation there. But the main feature is clearly associated with the geological terrain like cratonic region or more orogenic belt. And finally, if we look also information from magnetic anomaly, we can also see a very strong signal in Bangui region, so between the Congo and the Cameroon region, but also in South America, where we have the Amazonian craton. So the question now would be, what all this geophysical observation will tell us about the mantle dynamic and the physical state of the mantle. We look at all these data sets and try to use the sensitivity of these different data sets to have information about the mantle. What can we really see from geophysical approach? So with the large scale technique, imaging, what can we, how can we interpret this observation as a more smaller scale feature? Can we link the microscale observation? So it means by geochemical and petrological scale, so from rock sample, with the microscale imaging, and can we map the thermochemical structure on a large scale? So when I talk here a thermochemical structure, I mean information in terms of temperature, so one the temperature in depth, but also in terms of bulk composition of the mantle. So what are the main challenges if we want to quantify the thermochemical structure? So we know that the velocity anomaly on seismic tomography map cannot be explained only by thermal anomaly. We need to combine seismic observation, gravity information to have an idea about the density variation, and also thermodynamic modeling to have an idea of the relationship between velocity, temperature, and the bulk composition. But we need also address different problems, such as the non-linearity problem here. So it's not easy to convert velocity to temperature and bulk. We need also think about what kind of thermodynamic modeling we want to use. So we need to link the geophysical observation with the thermodynamic law, with respect of the Maxwell relationship. There was also the non-unique solution in composition space. I will back to this topic just on the next slide. And also we have also to deal with the trade-off between temperature and composition. What will be the main effect will be more temperature or composition. And the last part we need to think about is the attenuation, so analyticity and melt in water. So these three parameters play a role in thermochemical structure. And it's so straightforward to get this information from the data, basically. So there are a large uncertainty of this three information. So here just a slide about the non-uniqueness composition space. So for some of you are not very familiar with mantle geochemistry. So we generally represent the chemical composition of the mantle with measure elements, representing here in terms of oxide. So they are the silicium, magnesium, aluminum, iron, and calcium. And to better understand this non-uniqueness of the composition space, we can look at the result of Alfonso et al. 2013, where they use a Monte Carlo sampling method of the composition space for a specific property, so velocity and density. And as we see on this figure, each black dot represents sample with almost identical physical property. And we can see the range of the composition of at the end is very wide. And the star on the figure here is the target. So if you compare this pattern with the natural sample, so it's represented by the dash line on each figure, we can see that the sample, there are some samples are outside or inside this envelope. And if we combine this information for each oxide, we can start to reduce the number of solutions. So basically here, the whole message we need to have here is the composition space is not unique, and we need to use prior information if we want to reduce the number of solutions there. So if we think about more how we can deal about trade-off between temperature and composition, the only indicator to discriminate one from the other is to have independent information of the bulk density and the velocity. So if we look at the gradient of this ratio and comparing the gradient of density And velocity will tell us if the anomaly we observe is more a temperature effect or is more a composition effect. So if density and velocity behave in the same way, we observe is more a temperature effect, like on the right one, on this figure. But if they are anti-correlated, we have a composition effect, like on the left one, on this figure. So now move on. Just a very quick slide. This is a slide about the modeling approach. For some of you are not very familiar with the method, so we generally collect what we call observable. So observable is any data set we want to use. So it could be geophysical data sets like seismic, gravity, magnetic anomaly. They could be also geochemistry information. And we want to draw a cartoon to explain this observation. So what is it, the model? So depending the way we want to solve the problem. So if we start from the observable and we want to build the model, it's what we call the inverse problems. And if we start from the model and we try to fit the observable, is what we call the forward problem. So depending the problem we want to solve and the technique we use, we will properly select one or the other to solve the problem. So for example, if we work more in a probabilistic approach, we probably work more in forward problems. So we generate a series of models and we try to fit the observable. If we are dealing more with one data set, like a seismic one, we generally use more the inverse approach and we just try to generate a model associated with the observable there. But the main parameter we need to care about is what we call the misfit function. Is the difference between the observable and the model. So it can tell you how close or how far your model are of the observable, and also give you a first idea of the robustness of your model. Here, a very simple slide to try to explain the probabilistic inversion approach generally people use, and the technique we use in this thermochemical tomography approach. This is the most fancy, expensive one. So it means we need to generate a lot of model. So in our case, for example, we generate like more than a million simulation to explore the model space. So the blue dot, the blue square is the model space, and every dot is the way we just sample the model space. So it's around what we call a random walk. Where we explore the model space, we also need to have some prior information to solve the non-uniqueness problem, because otherwise it's very hard to explore. We can spend a lot of time to find the best, where is the best model to explain the observable there. And everything is represented in terms of probability density function, as you can see on the top left here. So here is just the basic Bayesian theorem we use in probabilistic inversion approach. So we need to use a prior. So what we start with, what we believe to be the model, and then we update this model, is what we call the likelihood. And every time we generate a new model, we look at how the probability density function look like, and depending if it's what we want or not, it will be accepted or rejected. And at the end, what we get is what we call the posteriori information there. And then there are also different techniques to sample the model space. And in our case, we are using the Metropolis Hastings algorithm, and we combine what we call the delay rejection and adaptive Metropolis technique just to speed up the way we sample the model space. So what is the technique we use here to constrain the thermochemical structure from a geophysical point of view? So is the joint inversion and petrological modeling approach. So what the community we call the leak mode approach. So the idea behind the leak mode is to combine different scale feature and information. So from the model we produce, we need to explain what the geodynamic process tell us. We need also to link these geodynamic processes with physical law, so mineral physics, thermodynamic law. We need also link with what the microscale observation tell us, so from petrology, mineralogy, and geochemistry information, and then what the geophysical large-scale feature show us. And everything is combining in a way we can explain the observable. And because this is no unique problem, and there will be many models can explain the data, we are using a probabilistic approach here. So how this lit mode work? So we are using a 3D block, and we divide this 3D block in 1D column. So here is just the example how we discretize Southern Africa, Central and Southern Africa. So we divide in 1D column. So in this case, we discretize like more than 1,000 1D column, and we assign at each dot geophysical observable. So I'll be back in the next slide what I mean by geophysical observable. But each observable will be sensitive of a specific physical property, and combining this complementarity set, we can constrain the 1D geotherm and the average bulk composition from this joint inversion. So for example, for Africa and for the grid resolution we work, we involve more than 40 million simulation for this scale of thermochemical tomography here. Just back to how we constrain how we discretize the temperature at each node. So generally we have the crust and the seismic moho. And then we have this LAB isotherm. So the LAB here is defined by the isotherm 1250 degrees C. And this is how we define the base of our lithosphere. And down is what we call the sublithospheric mantle, and is between the LAB isotherm and 300 kilometer depth. Is how we constrain the thermochemical structure in our case. We don't explore deeper than 380 kilometers. So everything is from surface down to 300 kilometers. And every black dot is where we invert for the thermodynamic information. So what we need to solve the free Gibbs energy. And then the red dot here is the fine mesh discretization for the 2 kilometer fine mesh to constrain it's just interpolation from surface where we have from surface down to the MOHO, and then from MOHO to LAB, and then from the LAB to the 380 kilometers. But if we want to have more detail about how is discretized in terms of the isotherm, we can discuss later about that. So how the lit mode work? So what is behind the lit mode one? So we are using a geophysical data set. So the geophysical data set is the elevation, the absolute elevation. So we are using also the geoid anomaly. They can provide some constraint on the density on the mantle. We are also using surface heat flux to constrain the thermal structure for the crust and get little constraint of the temperature at the MOHO depth. Then we are also using crystal model. So crystal model here is having information in terms of the crystal thickness, so the MOHO depth, but also information of on the lower crust, middle crust, upper crust, sediment thickness and sediment. So we need to have thickness, velocity, and density for each layer we are using here. And we also use Rayleigh wave dispersion curve to sample the mantle here. So everything for the surface wave is just the fundamental node to have an idea about the uppermost mantle. We are not interested outside of the uppermost mantle. then we use a geochemical and thermodynamic information. So we're using a full mineral physics database. So this database is from the Schichterud and Litko-Pertelloni database. They provide the thermodynamic information for the upper mantle. So we are using the system calcium, iron, magnesium, aluminum, and silicium. So what we call the SFMAS. And the main mineral here is olivine, cyanopyroxene, orthopyroxene, and olivine phase, so garnet, spinel, and pleasure clays. And everything here is written in a way the thermodynamic can explain what the geophysical observation tell us, and link this with microscale information. And then we need to solve several forward problems. So we need to solve the 1D steady state heat transfer, the free energy minimization, so the Gibbs one, the isostasy, the 1D geoid, the dispersion curve, and the attenuation also. So now move on the results. So as I explained you earlier, here we are working in a probabilistic framework. So we are generated a series of models. So we simulate, for example, for one column, more than 300,000 models. Then we just save 5,000 best model. And at the end, we just show the mean value or the median value of the best model for the region. So here I will just show you a series of figures and results we have for Central and Southern Africa. So Central Africa and Southern Africa is a very interesting region in terms of geology. They are composed of several cratonic blocks. So we have the on the right is the very simplified geological background. So we have the Gabon Craton on the west part of the Congo region. We have the Angola Craton. Then we have also the Kalahari and Zimbabwe Craton in South Africa and Zimbabwe. So if we go more in the north, we start to have the Benguelu block west to the Malawi Rift. Then more to north, we have the Tanzania Craton. These are the main block of cratonic domain in this region. But we have also orogenic belt. So we have the Damara belt in Namibia. More south, we move to the Namibia belt, and between Zimbabwe Craton and Kalahari Craton, we have the Limpopo belt. Then in this region, we also, if we go to the Congo, we have also this large intercratonic basin, the Congo Basin. If we go more east, we arrive in the East African Reef, where the lithosphere is stretching with the opening of a new crust and lithosphere there. And we have also very important shear zone, like the Central African shear zone between Cameroon and the Congo. And we also this very long lineament from Namibia to Malawi, what they call the Onga lineament. So they are very interesting feature in terms of geology, and it will be interesting to see what the thermochemical structure can be linked to this geological background. So here are the main results of our thermochemical tomography. So on the left is the LOB isotherm associated with the region. And on the right is the average bulk composition of the lithospheric mantle. So is the average from MoO to the LOB isotherm. So as you can see, there are very strong correlation between the geological background. So where it's very thick is where we have the Congo, the cratonic block. So in Congo, also in Zimbabwe, and in Cape Verde. You can also see a signal in Tanzania. So as we see, Tanzania has generally a thinner lithosphere there, but there are also very clear signal for the cratonic roots there, and also for the Benguelu block, so west to the Malawi region, we have also a very thick lithosphere. And if we go more north, so in Congo and in Cameroon, sorry, and in Afar, so more in Ethiopia and Somalia, is thinner lithosphere there, so less than 100 kilometers. And we can also pick some thinner lithosphere in Angola and in Namibia, and I will be back later of the meaning of that, if it's real or not. And if we move now more on the magnitude number, we can see also very clear signal in terms of where we have high magnitude number for the cratonic region in Cape Verde, in Zimbabwe, also in Tanzania and the Big Wheel block, and also for the Gabon craton. But one of the main interesting feature is for the Congo by himself, there are no this high magnitude number. And we don't know for the moment why the signal for the Congo is so different in comparison with other blocks in Africa. So now if we look a little bit, if we compare our thermochemical structure, so the present day thermochemical structure from geophysics with xenolith information, so thermochemical structure from geochemistry, and to see if we can map the same or if they are completely different, and if they are different, why is so different? So here, for example, is a comparison for a location in Namibia. So here is there are xenolith with the age of 71 million years ago. On the left, on the right one, the green dot are the xenoliths, and the blue line are the present day geotherm. So we can see there a shift between the present day and what the xenolith tell us. So today the lithosphere is thinner than 71 million years ago. And if we just look back in the thermochemical structure, is basically where we have a thinner lithosphere there. So then if we go more in the north, so 230 million years ago, we have the same pattern. So xenoliths show a thicker lithosphere than today, and it's basically in Angola there. So then if we look in South Africa, so for the Cape Verde region, so 9 million years ago, we can see that xenolith and the present day thermochemical structure are exactly the same. So the question will be why we have difference between Angola, Namibia, and Cape Verde. What's happened there? Okay. So if we look now the distribution of kimberlitic and carbonatite volcanism. So here is a panel with, on the left is the LAB isotherm map, in the middle is a magnesium number map, and on the right is the more depth map. So where we have the dot is where we have kimberlitic volcanism, where we have the square is where we have carbonatite volcanism, and the color associated with this circle and this square is in terms of age. So we are looking at volcanism younger than 2 million years ago. So if we compare this volcanism with, so one of the first information you can see that, for example, in the Kalahari region, so in South Africa, there are very intense volcanism there in comparison with the North Congo region in the last 2 million years ago. And we can see also there are a gap in terms of volcanism in the north of the Tanzania. So we have more carbonitic volcanism in the east part of the east of the Tanzania craton than in the south, where the south region of the Tanzania craton is more carbonitic volcanism. If we plot on this map the hotspot track across the continent, so we have the Tristan da Cunha hotspot, we have the Westmalle hotspot, we have the Cook hotspot. They cross the continent, and we can see where we have by the past. So we have erosion of the lithospheric mantle in Angola associated with this Tristan hotspot about 120 million years ago. They can explain why what the xenolith tell us is different with the thermochemical structure of today. And what we observe also in Namibia could be also associated with the Vesma hotspot. They affect they erode the lithospheric mantle beneath the region there. And if we look at Val, there is no hotspot where we have this the sample of the xenolith and what we have today. But if we compare what the magnesium number map from Geophysics, so is the map in the middle, with what the magnesium number is computed from xenolith, we have also very good correlation between what we map with only geophysical information, what geochemical observation can map. And we also be able from this technique to extend the mapping of the bulk composition of the mantle by using geophysical technique here. And then if we just look at the 3D view of the region, so this is a 3D view in cross-section beneath Central and Southern Africa. So the dots here are the kimberlitic volcanism, and the square is the carbonatite volcanism. So we can map, as we know, the Afar hotspot in the north of the region, and where we have no volcanism in Tanzania, so the north of Tanzania, could be associated with a downwelling in this region. They exactly match well where we have this downwelling, so no volcanism associated with downwelling region. And if we also look more south, we can see this hot apolic mantle associated with the shoulder around the Congo of the Tanzania craton here. And to finish with the Africa part, if we also look at quickly magnetic anomaly, so the Bangui anomaly between the Congo region and the Cameroon, we can see also a very interesting correlation between the magnesium number. So the dashed line on the map are the magnesium number, is a contour of magnesium number. So we have high magnesium number in this region where we have this high anomaly near the Bangui region. And if we just put on the map some geological background, is also the region where we have this Alakogen region, so the Sanaga Alakogen. So the Alakogen is where we start to stretch the lithosphere, but they never finished to open and generate a rift. So it's the incomplete stretching of the lithosphere there. So for the moment, we don't know how we can interpret the relationship between this anomaly with this high magnesium number. But if there are some people in the audience have some comment, I'll be happy to discuss with too. So now very quickly, what about South America? So South America was 200 million years ago connected with Central and South Africa. So here, a very quick background. So in South America, we have two main cratonic blocks. So we have the Amazonian block with on the north the Gondwana shield and the Guapore shield, and we have the San Francisco craton. So San Francisco was connected with the Congo craton 200 million years ago, and we have also this Rio de la Plata craton where we don't really know well where are the limits and the size of that for the moment. And we have this very clear trans-Brazilian lineament. So we know also if we look at the volcanism and carbonatite, the region also is different as Africa. So we have on the right is just a hotspot track across the region. So we can see the hotspot affect more the northern part of the Amazonian craton 200 million years ago. And they affect also a little bit the San Francisco craton, but no effect of the south part of the Amazonian craton. And on the right is the volcanism, so kimberlitic and carbonatite volcanism associated to for the last 200 million years ago of the region. So here is just data available. So it doesn't mean there are no more volcanism in Southern America. It just means we have no access or more information about volcanism beneath the northern part of the Amazonian craton here. But we can see, again, there are very strong correlation between volcanism in South Francisco and the hotspot track in southern San Francisco craton here. So I will not show you any thermochemical imaging of South America because we have just preliminary results and it's not complete and it was just very quick. But I will show you very quickly what we can see later. So now if we just finish with just a paleo reconstruction of the last 2 million years, we see that South America was connected with Africa, and in the south we have the Antarctica continent. And here the blue dots are the location of the hotspot. So if you think about what we observe in Africa in terms of thermochemical structure and the effect of this the effect of the hotspot on this thermochemical structure, we can ask ourselves what will be the effect of this hotspot on the thermochemical structure in South America, but also in Antarctica, where we know on the east part is a quatonic domain, and the hotspot affects the northern part of the East Antarctic craton here. So to finish and sum up here, so just show you on here very quickly. So on the top left is the thermochemical structure associated and to comparing South America with Africa. So the Africa one is complete, and the South America one is just preliminary result. But you can see already a very clear correlation relationship between Africa and South America in terms of thermal structure. So this approach helps to fill the better gap of the thermochemical structure of the mantle from geochemical approach. So we see we can have large scale view of the thermochemical information. So from this approach, we also provide new model for Central and Southern Africa. The plan will be also to provide model for South America and Antarctica. So my project now is working more in Antarctica. So the idea is to try to get similar figure and observation for Antarctica as I provide for Africa. And there are also some team working in Australia to get information for the Australia, and the final idea and output of the project will be to compare the thermochemical structure of South America, Africa, India, Antarctica, and also Australia. So in terms of my work here, so the next step of this work will be to solve the 3D problem here and include more constraint on density variation. So adding gravity gradient and body wave, because everything I show you today is just a 1D thermochemical tomography. But if we want to have better view of the density variation, we need to work in a 3D view. So we already run model, and we have a model for the southern part of Africa by adding gravity gradient and also ambient noise information. So this to update the custom model. And here just some reference. So we have, so there are 3 main papers to explain the technique, and they are also from Alfonso et al. And also on the top is the paper we will produce in the next few months for Africa. So the first one will be a paper we will submit in probably 4 weeks, and then there are some paper I'm working on to complete the project before the end of the year. So if you have any question or comment, we can ask now, or you can send me an email. And just a very quick announcement. So this year, the Geological Society of London have a new open access journal. And if you are interested to submit contribution for this special issue, ASA and Society, we can have a look at the website. We can get more information about this special issue. And if you have question too, you can also send me an email. Thanks.
Thank you. I'll applaud for everyone. Thank you very much. Are there any questions for Dr. Ben Mansour? There are virtual applauses for you. Oh, Harriet Lau, would you like to ask your question?
Hi, thank you so much for the talk. I was just wondering, it's really cool to see your finds on cratonic evolution, because as geophysicists, I guess we always just have information today. So it's really nice to be able to like think through time. Just process-wise, how do you envision, like, so you showed us the thinning craton, right, over time. Should we think of that as more, you know, when you talk about cratonic erosion, is it actually material from the lithosphere being eroded away through advection, or is it more that, like, you know, a plume impinges and it heats the lithosphere? So basically rheologically and mechanically, it's just heated up. So it's actually, at least in its mechanical properties, thinning because the base of it's just heated up so that it's less rigid, I guess.
I think it would probably depend on the thickness and the rheology at the time the plume arrived there to erode. Or if it's very thick and strong, with more mechanic one, I think it would probably depend how long also the hotspot would stay there. So probably it's a mix of both.
Right.
The only way to solve that is probably do some modeling and test different scenarios to have a better idea about the thinning. And then we also think about the bulk composition, because we always think about the thickness, but also the bulk composition can change. And for example, when you just look at the Congo craton, we always talk about the Congo big craton, but at the end, if we just look at the bulk composition for the Congo, there are no this high magnesium number for Congo. And this is also very strange. If you look Cape Verde or Tanzania, is very strong signal. But for the Congo, there are different blocks, but the Congo by himself have no signal. And if you just look the volcanism associated with the Congo, there are also very few volcanism there. So, yeah.
Okay, cool. Thank you. Yeah, because I just think when a plume impinges, on the one hand, it's hot, and so it's not very viscous. It stresses it, you know, places on the craton. You can't, you know, you have all these studies by people like, you know, Jason Fitzmorgan that shows the fingering of plumes rather than the plume actually eroding a craton. So it's, yeah, but you're right. I think it depends on the time scales that are at play.
The time scale, the size of the plume, thickness of the roots, shape of the roots.
Right. Yeah, indeed. Thank you. Thanks.
Thank you. Are there other questions? Oh, yes, Dr. Shankar.
Yeah, this is very interesting and exhaustive lecture. I have some queries about the data set, geophysical data set. I just wanted to know the data set he has used, that surface heat flux, elevation and geodetic anomaly, crustal model, and surface wave.
Yes.
So what contribution of the surface wave were there in your modeling? Surface wave.
So what's the contribution of the surface wave on the model?
Yes.
So your surface wave will basically control your thermal temperature, because surface wave will be affected by attenuation, and attenuation will be affected by temperature. So if your surface wave is completely off, you will get completely off thermal structure, depending how you compute your Rayleigh wave fundamental mode. If you are a wrong surface wave dispersion curve, your thermal structure will be wrong. So everything is basically controlled by your mantle, and the mantle is controlled by seismic, and the seismic is controlled here by Rayleigh wave fundamental mode.
So you have used the what component of the surface wave, velocity or frequency of the waves?
So we are using the Rayleigh wave fundamental mode.
Rayleigh wave.
Yeah, it's the Rayleigh wave. So depending if you combining earthquake or ambient noise. So if you have no ambient noise, probably 25 seconds to 160 seconds.
Okay. And another query is about the a period of the data, how much period of the geophysical data you have used?
How many what, sorry?
Length of the data, period.
The period, how many periods?
Yes.
Oh, you need to have between 90 and 23 periods, but you need just have a very sample, your dispersion curve. Because you need to fit the shorter period, but also need to fit also the longer period.
Yes.
You have a balance between your short period and your longer period. Generally, if you just you have your dispersion curve, there are more periods for shorter one than longer one. And if you want to fit everything, you need to have the balance. Otherwise, you need to put weights between the longer period and the shorter one.
Oh, okay, thank you. Thank you. So nice of you. Okay.
Thank you very much. Oh, Jeroen van Hoon, would you like to ask your question?
Hi, Walid. It was a very nice talk. Thank you. I was just wondering if you have any further thoughts on the significance of these magnetic anomalies you talked about around Cameroon and Congo. And I was intrigued by it. I don't know a lot about it, but I was just intrigued. So I was hoping to get some more info.
So with Juan Carlos, we compare the thermochemical structure with every geophysical observation we observe. And I found one day magnetic anomaly map. We map on that. And we don't really know how we can interpret it. Magnetic anomaly could be from the crust, but it could be also a deeper signal. So if we also look what we have in South America, we have also a signal there, less strong, but we also signal in South America associated with this Bangui anomaly. So at that step, we have no response about what could be the reason for that. But so it would be interesting to talk with people who have more experience about magnetic anomaly, interpretation, how they process the signal, where could come from the signal, if it's shallower part or deeper part, what would be the size of that. But in our framework, we don't invert for magnetic anomaly. But the signal is very clear, and they fit well where we have the very clear shear zone there. But what the correlation between this anomaly with the magnetism, the bulk of the lithospheric mantle, yes, is very, very strange and interesting. But no, I don't know, sorry.
Yeah, well, as you say, I mean, it looks like from what you showed, it also seemed to kind of continue into South America. So if you would put the two continents together, it looks like this anomaly seemed to fit together. So yeah, maybe it seems to suggest that maybe this is a feature from pre-opening of the South Atlantic. Then.
Yes, they fit together, but the amplitude of the Bangui is larger than the South America one.
Oh, I see. Okay. Okay.
So
thank you.
It could be from volcanism there because he also fit with the Gabon craton there. So yeah.
Great. Thanks. Thanks.
Modeling, I guess, to test some model there. But from geophysical observation, it's impossible to explain that only.
Thank you. Thank you for the question. Are there other questions for Dr. Ben Mansour? Oh, Harriet, do you have another question?
I don't have to ask if there are any others since I've already had my turn. But I was just, if I may, I guess, if there are no other questions, it was cool. So you were kind of, for each little point, this is more methodological, you were solving for a 1D profile, right? And did you impose any kind of lateral covariance between, you know, one profile here and one, because it's quite impressive how coherent they came out.
So for the LIT mode 1, there are two codes. So the first part of the project was to use just the 1D1. So there are no communication in between.
Oh, right. And yet you still had quite coherent, like at least laterally coherent, which is quite cool given that it was a Monte Carlo.
Yes, if we want to connect both, we are using the 3D1 and we use body wave and gravity gradient. And in this case, we can have a connection. And the difference is very small. There are no huge difference. So the 1D approach and the 3D is very similar.
And so with the 3D approach, I was just wondering, I think the result you said you had like 41 million simulations or something like this that you played around with.
Yes.
And that with the 1D, how would that change with your 3Ds calculations?
I think not that much because there are someone implement and improve the code. So it's look like we need, for example, for the 1D, we run for one column, we need 12 hours.
Right.
12 hours. So it's very fast for Bayesian inversion. When you think we generate more than 300,000 model, is very fast. And the 3D, we need probably a week.
Right.
2 maximum for.
Yeah.
Very fast.
Yeah.
So also using a delay projection technique to speed up. Inversion.
Yeah. I wonder if you can feed your 1D results in as some sort of prior or something like that to kind of narrow down.
Yeah, because for the 3D one, we are using as a prior model the 1D result.
Okay, yeah, right.
Start with the 1D to get the prior for the 3D one.
Mm-hmm.
Too long.
Yeah, I was just impressed how coherent the 1D results seem to be anyway. It's cool.
I'm also very impressed by that too. But
yeah.
No communication and if it well.
Mm-hmm.
Oh, yes, Dr. Shankar, you have another question?
Again, I have some confusion because I am not fully understanding your talk modeling. So again, on the topic surface wave contribution, since surface wave are generated on the surface of the earth or few meter depth below the surface of the earth. So how it contribute in your modeling on this mental level?
Okay, so the approach we are using is a John inversion.
Mm-hmm.
We need to generate a model for each data set. So for surface wave, for heat flux, for topography. We try to fit every data set. So when we have a model, they fit, for example, elevation, we are looking if the model, they fit also surface wave. And the idea is to fit every data set in the same way. So if we just use surface wave, you have a model for surface wave. And your surface wave, it just control what we have in for the mantle. Is because in joint inversion, every dataset is sensitive to different parts of the model. Your surface wave will be sensitive to the mantle. The topography will be sensitive more to the crust. The GOE will be sensitive to the mantle. So, and the surface wave, we have started at 25 seconds. So we are sampled also the crust because the crust there is in 40 kilometers, most of the continent, or the more south is 50 kilometer thickness. But we are sampled the base of the crust and the uppermost mantle there. But if you invert your surface wave only, it will fit also, you will also produce a model, and then you need to convert in temperature there. So I'm not really sure what I missed to explain the approach, because your surface wave don't really control only the mantle. Your surface wave will control the temperature, because surface wave will be sensitive to temperature variation. That's it. The other information, density or topography, are not affected by temperature. And the only way to affect your temperature is to play with your surface, your shear wave velocity here.
Okay, thank you. Thank you.
Are there any other questions?
Hello, yes.
Go ahead.
Thank you, Walid, for an interesting talk. I have a question about the modeling of the 1D temperature profiles.
Yes.
Does the composition, are the variations in thermal conductivity significant enough to have to be included? Or can you assume that all the compositions have the same thermal conductivity?
So for each layer, we have the same for each block. So the thermal conductivity will be the same yeah, maybe the same. There are no big effect of that. And the approach can really solve just for the cratonic region. So we need to be in steady state. So if your profile just drop and for increase, just break the assumption behind the approach there. But no, everything is constant there.
Okay, thank you. And related to that, are there large uncertainties in the radiogenic heat production, and are they included in your uncertainty estimates?
So the radioactive production, yes, because we provide that as a starting point. And there are little variation, but not that huge. So yes, they modify a little bit, but not a big one. Yeah, I can have a look.
Thank you.
Also send you some result if you want.
Is this work published? Perhaps I could read up on it.
So the paper will be submitted probably in 4 weeks if my co-author will be happy. We were running on that paper last year, so we are waiting, pushing. So
cool. Good luck with that. I'll look out for it. Thank you.
Are there other questions? Gaia, did you have another question? Actually, Walid, I just had a quick one then about the method. How much of a difference does the type of crustal model you use make to these results?
So for the crust, so we discretize depending of the sediment layer on the top, because sediment will affect your modeling and affect the gravity information there when you invert. So for example, for a region with large sediment layer like the Congo Basin, so we have probably, we have 3 layers for the crust, and the other region have just 2 layers for the crust. So if we have sediment up to 2 kilometers, we just separate that and we run it. But there are not huge difference because we are looking more for the base of the moho. So the upper part of the model are not sensitive with the data we use, because the upper part need to be fit with dispersion curve, and our dispersion curve never starts for the shallower part. So if we are sediments, they need to be very, very thick to affect the model at the end. And if we want to play more with the shallower part of the crust, we need to include gravity. So looking at more the 3D part, so gravity gradient, including ambient noise. And then we can play a little bit with this shallower part of the crust. But otherwise, the model are more sensitive to the base of the crust, so lower crust, middle crust, I would say. But there will be a big difference. The only difference will be where is your, and the more temperature will affect a bit your LAB depth there, and your composition too, because more depth, LAB and composition are related there.
Right. Okay. Thank you. Are there any last questions? And if not, let's thank Dr. Walid Ben Mansour for a great talk, good discussion.